Let's discuss sound intensity. I show at the center of a sphere a sound source, a speaker, that has an output power P. Power is measured in watts. A distance R from the source of sound is an observer, a listener, a sound detector. The amount of sound at a particular point can be quantified in two different ways. We're going to discuss the first of those two ways now. That first of the two ways to quantify sound is called sound intensity, labeled I. The value of the intensity of sound at a particular point, a distance R from the sound source, is the output power of the source, P, measured in watts, divided by the area over which that sound power is distributed. At a distance R away from the sound source, we imagine a sphere of radius R. The sound source is at the center of that sphere. That power is distributed uniformly, we assume, over that spherical area. We're talking, therefore, about a source of sound that's called spherically symmetric. It broadcasts power equally in all directions. Here we have then the definition of sound intensity at a particular point R away from the sound source. It's the output power of the source divided by the area of the sphere. The units of sound intensity, therefore, are watts per square meter. So far, so good, I assume. Let's work a simple problem, an example problem, shown here. Suppose at the first of two locations, the first one being labeled R1, an observer, a listener, is 3 meters from the sound source, and an intensity measuring device records that the intensity, labeled at I1, is 6 watts per square meter. We ask the question, what is the sound intensity at a second location? What is I subscript 2? Given that the distance from the sound source, R subscript 2, is 2 meters. Well, there are a couple of ways to solve this problem. I'll show you the first of the two ways and talk about the second. Experience tells me that if I form the ratio of the intensity expressions, I2 over I1, an unknown quantity, the output power, will vanish from the equation I create. That's good because the output power of the sound source was not specified, so we better create an equation that does not have P in it. Here we go. The ratio of the intensities is shown here. This is I2 at R2, and that's I1 at R1. Notice the P's cancel. They're not subscripted. There's only one P in these two situations. The 4 pi's also cancel out. And you're left with the R squareds, which reciprocate in this manner. In the parentheses, we have the ratio of the R's squared. And the I1, I move to the right side of this equation. And now we substitute. R1 is 3 meters. R2 is 2 meters. You squared that ratio times I1, which is 6. This is 9/4 times 6. Final answer, 13.5 watts per square meter is intensity at this point R2, which is closer to the sound source than first listener was. And you expect, therefore, that the closer listener should experience or detect the greater or the higher intensity, which is what happened here, 13.5 watts per square meter versus 6. So it seems to make sense. Now let's talk about the second of two ways to quantify how much sound there is at a particular point. We began by describing a thing called the threshold of human hearing. The threshold of human hearing is, on average, for a healthy human ear, it's the least sound intensity the eardrum can detect. It's the amount of sound intensity you expect on an early fall morning before there's any traffic in the streets. A maple leaf flutters to the ground, strikes the grass. A listener 1 meter away is listening for the sound of that leaf landing on this silent morning grass. That's the threshold. Now, it's measured to be approximately that much, 1/1,000,000,000th of a watt per square meter, 10 to the negative 12. Well, we'll use this threshold number to define a quantity called the decibel level. Decibel level. It's also called the sound level. The decibel level is defined by this equation, where lowercase b, Greek, is beta. Beta is 10 times the logarithm to base 10 of the ratio of the intensity here divided by the threshold intensity. The units are dimensionless, but we nevertheless have a word for that dimensionless quantity. It's called a decibel. And so the standard international units for sound level, also called decibel level, is the decibel, labeled D, uppercase D. Let us, before we continue, note the following. It will be expected that you know that the logarithm of 1 is a 0. So imagine that the intensity at your eardrum or at some measuring device is equal to I naught. So you'd have in this ratio I naught over I naught, that's 1. The logarithm of 1 is 0. And so the decibel level in such a case is 10 times 0 or 0. In such a case, we see we have the right to put a 0 subscript on this threshold. At the threshold of human hearing, at that intensity, beta is 0. The beta associated with this sound intensity at your ear is 0. That's why we put a subscript 0 on the I, to remind us that at that sound intensity, the decibel level, beta, is 0. Let's work a simple problem. Through measurements, we've determined that the average conversation between humans, separated by about 1 meter apart, hello, how was your morning? What are your plans for the rest of the day? That sort of conversation provides at the listener's ear an intensity of about 3 times 10 to the negative 6 watts per square meter. 3 microwatts per square meter. What's the corresponding decibel level? Simple calculation. Beta is 10 times the log of the ratio of I to I naught. rounded to the nearest whole decibel. The decibel level that you experience in normal conversations is about 65 decibels. In the next video lecture, we'll look at some other examples of decibel level problems. I'll let you look at what's on the whiteboard for a little bit so you can review the things that I've told you. Play bumblebee. That's all for now.